Welcome to CS420, lecture number 6. In this lecture we're going to talk a lot about recursion. But to start, we're going to just review what a data type is. A data type is a set of values and a set of operations that we can perform on those values. For example, we have a data type of a number. So, we have different numbers, 5, 7, 10, etc. And operations we can perform on it. We can add numbers together, we can subtract numbers, of course we can multiply and divide numbers. So that's a data type. Some data types are built into a programming language, like numbers, strings, booleans, etc. And other data types are called user-defined data types. And those are data types that you can invent yourself. And one way of doing that is by creating a new class. The new class defines a set of values, and those are the fields or the member variables of the object. And then you define operations that you can perform on that object. Now let's talk about inductively defined data. Inductively defined data means that we're using itself in its own definition, kind of like recursion. So if we're going to define a set of whole numbers, we could just say 0, 1, 2, 3, and so on, or use the ... Now that's really good for humans because they could kind of interpret that pattern, but it's not so good for programs or computers because they have a hard time figuring out what the pattern is. And even humans do. In fact, some IQ tests have people try to figure out what number is next in a sequence of numbers. Whereas inductively defined data uses itself in the definition. So 0 is in the set. If n is in the set, so is n plus 1. So hopefully we remember definitions like that from previous classes. Now BNFs are another way to define data inductively. And they're just context-free grammars that you might remember from a computer theory class. Now, in context-free grammars or BNFs, we have non-terminals right here. And when they're on the left side of this arrow, that means we're defining it. So what is a list of numbers? Well, a list of numbers is an empty list. Or, the little bar means or right here. It's a number paired with another list of numbers. Now the non-terminals are these HTML tag-like looking things where we use the less than and greater than signs to surround them. And the terminals are anything else. So we got the parentheses, the periods, and so on. And those are the terminals. Now, number would be something else we need to define, but we're just going to assume that everybody knows what a number is. Now let's do a syntactic derivation. A syntactic derivation is a proof that something is or belongs in a set. So take this for instance. Let's prove that that is in fact a list of numbers. So what we do is we start out with our non-terminal, and I am just going to write LON for short for a list of numbers. So we can replace an LON with either a empty list or a full list. And since there are numbers still inside of it, we're going to do a full list. So I'm going to replace that with a number paired with another list of numbers. Okay. Now the number I'm just going to replace with 4. And this list of numbers right here needs to be replaced with this part right here. So I'm just going to, for now, I'm just going to write list of numbers. And now in the next step, I'm going to replace the list of numbers with that part, with this part right here. So we got that from before, and now we're going to replace the list of numbers with 3 paired with another list of numbers. And finally, we need to replace this right here, this right here with this part right here. Well, that part, instead of being a full list, is now an empty list. So we can replace it with the empty list, which is just an open and close parenthesis. So each time we replaced list of numbers, we either replaced it with an empty list, and that happened at the end, or we replaced it with a full list that includes a number and another list of numbers inside of it. And by doing that, now we have the final result. So this is a proof that this is in fact a list of numbers. Now when our data is defined inductively or using a BNF, we can use its definition to guide us in writing programs that act on that data. Now this is list of numbers. I'm just doing LON for short. So we have a list of numbers is either an empty list or it's a full list. And a full list is a number paired with another list of numbers. And yes, we're using our pairs that we learned about a couple of lectures ago. So let's just do a quick review. Remember, cons creates a pair, so it has two parameters. And the first parameter is the first element of the pair, and the second parameter is the second element of a pair. And we also remember that car and whatever its parameter is, this better be a pair, and car will get us the first element out, and cutter will get a second element out. And we also have these box and pointer diagrams. So whenever we create a pair, we can draw a box, and by drawing this out, it can help us see what's going on. But car gets the first element out, and cutter gets the second. So once again, we have the BNF, or a list of numbers. And again, I abbreviated list of numbers to be LON. And now we want to write a function that operates on this data type. So I've written down some steps to create a recursive function that operates on an inductive data type. So whenever we have an inductive data type and we want to do some operation on it, we're probably going to be making a recursive function. And this is where we're going to get really good at writing recursive programs. Now you might want to write down these steps on a piece of paper or take a screenshot and have it available as we go through these next steps, because I don't know if I can show the steps and the code that's going to operate on this at the same time. But the function we want to create is a function that returns us the length of a list of numbers. We want to know how many numbers are in a list of numbers. So step one is to create a function for each non-terminal. So we're going to define list length to be a function that takes in a list of numbers as its parameter. All right, there's step one. Step two is to separate the productions. So what we want to know is this list of numbers that's passed in for my input, is it an empty list or is it one of these full lists? We need to know which one it is, because what we're going to do is going to be different if we have an empty list versus a full list. So to do that, we need to ask a question. So we're going to go if null list of numbers. So an empty list is also null. So if it is null, then we know that we have an empty list. So in this case, I'm just going to put a comment here saying that we have an empty list. And now, in this spot, if it's not null, now we know we have a full list. So now we know which one we have. We know if we have one of these or one of these. So now let's move on to step three. We need to break apart compound data. Compound data is where we have more than one value in our data. Now an empty list has no values inside of it, so that's definitely not compound data. But our full list does. It has two different things in it, and we need to break those apart. We need to get to each one of it. So that's where we'll use car to get this part and cutter to get that part. So the car is the number and the cutter is another list of numbers. All right, step 3 is done. Now we move on to step 4. We need to make a recursive call. So whenever we have data that is of the format of our non-terminals, right here, we need to recurse on it. And in this case, right here, that's a number, and we already know what a number is. But in this case, we have another list of numbers. Remember, the cutter is another list of numbers. So we need to make our recursive call on that. So I'm just going to go list length of the cutter. All right, step 5 is the hardest step. You should be able to follow steps 1 through 4 pretty easy. In fact, someone can even write a program where you feed in the BNF and then you automatically produce this much code. The hard thing is step 5. We have to combine results and return the correct answer. So let's try that with our empty list first. What is the length of an empty list? Well, 0. That's pretty easy. Now let's try our full list. And this is one element right here, and this is the rest of the list. But list length returns the length of the list. And this is one little trick when we write recursive functions, is we have to have faith that our functions already work the way they're supposed to. So I'm having faith that this will return the length of this smaller list inside. So we have one more element, so I just need to add 1 to the length of the inside list to get the right answer. So we'll just do +1. And you know what? I don't even care what the number is. That's not that isn't involved in this answer, but that won't be the case most of the time. This is a little exception, but I don't really care what the number is. I just know that I have one number, so that is going to be a length of 1, and I need to add the length of the rest of the list to it. And now we can close off all the other parentheses and test this out. And we'll create a list with, let's see, 4 elements inside, and it returns the length of 4. And what if we create an empty list? Well, it returns the length of 0. So now we want to do another example, but this time we're going to operate on a list of symbols, which is pretty much like a list of numbers, except for we have symbols instead of numbers. And the function we want to write is a function that removes the first symbol in the list. So it's a function that takes 2 parameters. One is going to be a symbol, and the other one is going to be a list of symbols. And so if this list of symbols has this symbol inside of it, we're going to remove the first occurrence of that symbol. So let's just see a couple of examples of what the input and output would be. For example, if we have the symbol A and a list with B, D, A, C, we want to remove the first A in this list, so the answer should be a list with B, D, and C in it, with the A removed. Now, if there happens to be more A's in this list, like this list right here, so notice there's 2 A's, we would keep the second one. So after this C, we would have the A, F, D. We only want to remove the first instance of the A in the list. So that's what we want this function to do. And we're going to follow those same steps that we did before to create this function. So we've already done step 1 and create the function. Now step 2, we need to separate our productions or figure out which kind of list of symbol do I have. Do I have an empty list or do I have a full list of symbols? So we can do that with the if statement we used in the previous function. If the list of symbols is null. And if it is, then we have an empty list. If not, then we have a full list. So step 3 is to break apart complex data. So in the case of an empty list, there's nothing to break apart. It's just an empty list. But this full list has a symbol and a list of symbols. So let's break that apart with our car and cutter. Okay, now that we've broken those two things apart, the next step is to recurse where we can. So notice we have the non-terminal list of symbols, and the symbol is a built-in data type, so we can't recurse on a symbol. But if this were some complex type, then we probably would write a recursive function to handle it. But in this case right here, we have a non-terminal list of symbols, and we need to recurse on it. So we'll just call our remove first. And make sure we pass in the right parameters. So remember, it takes 2 parameters. So we're still going to try to remove the same symbol from the second half of the list. So we'll just pass in S right there. So that was step 4, make the recursive call. And now we're on to step 5. We need to combine our results and return the correct answer. And we have to do it for both our empty list and our full list. So if we have an empty list and we want to remove something out of it, what's the right answer? Well, of course, we're just going to pass an empty list back. Now in this case right here, our full list, I'm going to separate out the 2 parts. And we got to trust that this remove first will do its job. It will remove the first symbol, whatever this symbol might be, in the list of symbols. We just got to do the job for this symbol right here. So if this symbol, and remember the car of the list is a symbol, and if that symbol is equal to the symbol we want to remove, then we should remove it. So let's go ahead and check. If our symbol that we want to remove from the list is equal to the car of the symbol, then we want to remove it. So what does it mean to remove it? Well, we're at the front of the list. The symbol is equal, this symbol right here, is equal to the symbol we want to remove it. So let's just not return it. Let's just return the rest of the list. And the rest of the list is just the cutter. So we're just going to return that. Okay, and that's the true if they are equal. If they're not equal, then we want to keep the car of the list symbols combined with the rest of the list, but removed out of there. So I'm going to remove this space here. So somehow I have to combine this guy and this guy together. And I have a list and I have an element. I want to add the element onto the front of the list. Well, if you go to your box and pointer diagram, all we have to do is cons the element with the rest of the list. Remember, a list is an element in the car position and another list in the cutter position. So now we can close all our parentheses and we're done. We have a remove first function. So let's see if it works. So we'll do that same example. So I might not get the same list, but D, C, A, B, F, A, D. And we can see that this first A is now removed out of the list, but we did keep the second A. So here's a very important question to see if you understand this. Why did we not remove the second A of the list? Why were we able to keep it? And if we wanted to remove all of the elements from the list, all of the A's, not just the first one, how would we change this to remove all of the elements? Now, the best way to answer those questions is to first understand how the element got removed. When the symbol that we want to remove is equal to the element, or the symbol inside of the list, when they're equal, we want to remove it. So how did I remove it? Well, what I did is I broke the list apart. Each recursive call takes the front element, or the first element, off of the list. So the first recursive call takes the D off the list. And then when we recurse, we're only left with a list from C through this ending D. Then the second recursive call takes the C off of the front of the list, and the rest of the list is there. The next recursive call takes the A off and leaves the rest of the list. The next recursive call will take the B off, and so on. So each recursive call takes the very first element off of the list. In this case, when the element is equal to the symbol we want to remove, instead of adding that element back to the list, we just return the rest of the list. Another way to say this is we're breaking apart the entire list, and when we get to the very end of the list, right up here, we return an empty list. And then we keep adding the elements, starting with the last D, back onto the empty list. Then we add the A back on, then the F back on, and the B. So as we rebuild the list, because I do not cons the car back on here, I rebuild the list without the A. So in this step, right, if I'm in this case right here, I take this list and I don't add the A back on, I just return it back, and then the C gets added on and the D gets added on. So because there's no cons right here is why the element gets removed. Now the other question is, well, why do we no longer remove the next A? How come this A got to stay on? Well, there's one other thing that I didn't do here. I didn't recurse. Notice I recurse on the cutter of the list. So as soon as I find that element that doesn't belong that we want to take out, I don't call remove first on the rest of the list. I just grab the rest of the list and pass it back. So this part never gets broken apart. We just return it back as soon as we find an element. So how do we remove all? So I'm just going to copy and paste this function and change it to a remove all. Now, whenever you do this, make sure you go in and change all the recursive calls, or else you'll be really confused, because the first recursive call will jump back up into this function right here, and now you'll be back to removing first. So whenever you copy and paste a recursive function, make sure you change all the recursive calls in it. So all we have to do to remove all of them is recurse here. So add in a recursive call, and now instead of, when we find this A, instead of just passing the rest of the list back, we're going to remove all the A's in the rest of the list. We'll get that list back, and then I'm not going to include the A. I'm not going to cons the A onto the front, but I'll return that, but the C and the D will get consed onto the front. So let's see if that works. So now I have another example. There's two A's in here, and they should be gone when we remove all of the elements, and you can see they're gone.